Welcome to a new episode of Quantum Conversations. I am Sophia from Girls in Quantum, and today I'm interviewing Bethany Terris, who just finished her PhD last year. So, congratulations for that. And I'm very happy to have this interview with you today. And you did your PhD in physics and philosophy, and I think that's so amazing. And maybe you can introduce yourself very shortly and then also like talk a little bit about your PhD. We'd
Yeah.
be very happy about that.
Yes, thank you. I'm really happy to be here. So, yeah, I'm Bethany. I defended my PhD this past November in philosophy of physics. But specifically, I was working in the field of quantum foundations. And prior to this, I had always had this idea in my mind that I wanted to go in this direction. My master's was in philosophy of physics also, and then my bachelor's was a mix of physics and philosophy together. So I always had this inclination that I wanted to combine these two topics together, and my PhD was really the culmination of that.
Wow, that's amazing. Mm, What's your PhD title? I think that would be super interesting.
So the title of my thesis was Weak Values in Quantum Mechanics.
Weak values?
Yeah. So
Oh, okay.
basically, weak values are the outcome of a weak measurement, which is
Yeah.
another way of measuring a quantum system as opposed to a standard projective measurement. And I can speak a bit more about it if you.
Yeah, maybe you can explain that a little bit at a lower level. For example, also for students who are like in high school or in middle school and just starting to learn quantum computing and quantum mechanics.
Of course, we know a very key feature of quantum mechanics is, sorry, when we measure a quantum system, let's say a particle, we get some information about it, but we disturb its state, and that destroys any further information that we can get. So you can think of that as maybe an analogy. Uh, let's say you have a friend who's blowing some
Mm.
bubbles. You're blindfolded, you can't see where these bubbles are. The only way you can find where they are is by touching the bubble. And once you touch a bubble, it pops, and that tells you the bubble was in this position where you pointed. But because the bubble was popped, you can't get any more information about its ongoing journey. Now, that's a bit of an analogy to our standard quantum measurements, but what I was working on is something called a weak measurement, which is um, a softer approach to measuring quantum systems. So instead, you can think of rather than blindly waving your hand around and trying to poke and pop the bubbles, um, instead, we can close our eyes and maybe blow into the air softly.
Mm.
And by gently blowing, we could get a teeny bit of information about where these bubbles are.
Ah,
But
I really love the analogy. That's so amazing. I remember that.
yeah. But yeah, we don't get the full information about the bubble is definitely located in this position. And so a weak measurement we can think of in a similar way. We measure a quantum system very, very gently. So between our measurement pointer and the system, there's something called the coupling constant, which couples them together. And we make that coupling constant very, very weak. And we receive a tiny bit of information about the property of the system that you're measuring. So maybe the position of it.
And do we destroy the state with that? So would we like pop the bubbles?
We do not pop the bubble.
Ah,
It's
okay.
as if we're gently blowing the bubble. So there's
Ah,
a
okay.
little bit of disturbance,
Yeah.
but a very small amount, which means that we can continually perform further measurements, whether they be weak or strong destructive measurements.
Okay, great. So what is the philosophy part about your PhD?
Yeah, so of course, as you can imagine, there are a lot of uses for these weak measurements, practical uses, but there's still this underlying question of should we even be using them to tell us about properties of quantum systems? Like, should we use them in the same way that we um, use strong measurements? So a weak value is the outcome of these weak measurements. And you can think of them as kind of similar to how we get an eigenvalue from a strong measurement. But the weak value, because it comes from this weak measurement, which is the result of having a weak coupling, and therefore the information that we get is very little with a high uncertainty.
Mm,
And so when we
makes
perform
sense.
these weak measurements, we have to perform them again and again over a large
Mm.
ensemble.
Ah, yeah.
The weak value that we get at the end is the result of measuring it over this large ensemble. So part of the debate concerns whether weak values actually tell us anything meaningful about the system
Mm.
at all, or if they're just something statistical.
Yeah.
So, the first chapter of my thesis was, well, the second chapter of my thesis was about this debate about what a weak value is, and whether it's something that is statistical, whether it tells us about a real property of a system, or perhaps it tells us something a bit more structural or contextual. So this is the main philosophical debate that is ongoing, and there's no clear answer. It's more so interpretation based. Um, but there's also a number of questions that result from weak values and weak measurements that are quite philosophical in nature. So, by performing weak measurements, we end up with a bunch of quantum paradoxes.
Mm.
For example, one such paradox involves measuring the position of a particle in an interferometer and weakly measuring, by the way. And by doing so, we end up deducing a discontinuous particle trajectory. And so some people can be fine with this and they just say, well, this is just another quantum feature. But part of my thesis was to investigate this paradox and see whether there's a way of resolving it and returning to a more classical way of thinking of particles following continuous trajectories. And I found a way of doing that using something called a sequential weak measurement. When you perform a weak measurement, we have to pre and post select the system. So we have to choose an initial state that it's prepared in, the pre-selection, and a final state that we want it to end up in. And we discard all the other
Mm.
results that could possibly happen. And the weak value is found by conditioning on these pre and post selections. A sequential weak value is found by conditioning on these same pre and post selections, but performing multiple weak measurements in between.
Do you use quantum operators for that?
We can, but we can also calculate it from the weak value equation
Okay.
by doing this conditioning. So my general idea, my general argument in the thesis was that these sequential weak values contain this cross-time information
Oh, that sounds complicated.
that allows us to track the evolution of systems in a way
Ah,
that the single time weak measurements uh, destroy due to the immediate pre and then post selection surrounding them.
I think especially time evolution is like a very big topic in like quantum computing and like because quantum computers can calculate the time evolution of states better than normal computers can.
Mhm.
Yes. Wow. But this is so cool. This is so interesting. Well, so thank you for explaining that. Um, Okay, and now I have another question for you, more like regarding quantum computers and its futures in its future. Do you think now, as a PhD in quantum, that like the economic side of quantum computing may be a little bit overweighted? What is your opinion as an expert on that?
I can see that there's a lot of need to hire in the quantum industry right now,
Ah, okay.
and there's a lot of promise around what quantum computing can achieve.
But that's good to hear that I know there's lot of people to be hired in quantum, so that's like
Yeah.
a good future for
Yeah.
us girls in quantum. Okay, so thank you for so much. This was super interesting, and I think I'll talk more about it with you. And yeah, thank you guys for watching, and have a nice day. Bye.
Bye bye. Thank you for having me.
Yes.